Welcome back to this course on Introductory Statistics. Today we're going to get a little bit more in depth on descriptive statistics, which are numbers that concisely summarize the variables in your dataset. The learning objectives for today are to teach you about different measures of central tendency, which tell you what value is typical for the participants in your dataset, and we will cover the mean, median, and mode as measures of central tendency. And we will cover measures of variability, which tell you how much people's scores differ within your dataset. And we will cover the range, variance, and standard deviation as measures of variability. Finally, for all of these measures, we'll look at the effect of transformations and outliers so you can get a sense of how blanket transformations of all scores and changing one individual score in the dataset affects these measures. In the previous lecture, we covered variables, and you know that a variable is a quantity that can take on different values. If you measure those values in a sample, then you obtain data or scores. So imagine that my variable is students' grades for this course, and I might have obtained the scores that you can see on the screen now. So one student obtained a 6 out of 10, another obtained an 8 out of 10, yet another obtained a 5 out of 10, etc. Now I want to introduce the concept of a distribution. The distribution is the general shape of these scores. So I can keep listing all of the scores of the participants in my sample, but wouldn't it be more convenient if I could just tell you what they look like in general? That's a distribution. So one way to summarize the distribution of student scores is by computing a frequency table. Because scores are a discrete ratio level variable, there are only a limited number of unique values that occur in a sample. Any score between 1 and 10 is valid for grade. So here's a table where you see that students obtained the grades of 3, 5, 6, 7, 8, 9, and 10. And we see how frequently each of these scores occurred in my sample. So there was one student who got a 3, but there were, for example, 6 students who got an 8. This bodes well for this year's cohort. A way to visualize such a frequency table is by turning it into a bar chart. In a bar chart, each discrete value is assigned its own bar or column, and the height of that bar is determined by the number of participants that obtained that particular value. So here below in the slide, you see all of the scores that I just showed you in the frequency table. And again, we see that only one student obtained a 3 and that 6 students obtained an 8. In a bar chart, it is conventional to keep a little distance, a spacing between each of the bars. And this is done to visually communicate that the scores are discrete so that there is no continuous movement from a 3 to a 5, for example, but that those are two discrete different values. I emphasize this point about bars being separated in a bar chart because now I want to introduce you to the histogram, which is a chart that looks visually very similar to a bar chart, with a key distinction being that now the bars are touching. And this is because the histogram is actually used to summarize continuous scores. Imagine, for example, that instead of grade, I measured all of my students' heights. Height can take on any value. It could be a value in centimeters, could even be rounded down to millimeters. So they can take on any number you could imagine. The problem with this is that we, of course, don't want a separate bar for every unique value of height, because no two students are going to have exactly identical heights, so every bar would have the same height of one observation. It would be very inconvenient. A histogram solves this problem by first dividing the number line into equal segments. These are called bins, and then counting the number of participants that fall within each bin. So here we see that there is one bin that ranges from about 140 centimeters to 150 centimeters, and we see that one student fell into this bin. And we see that there's a bin from 150 to 160 centimeters and 2 students fell into that bin. And we see that the most common height is somewhere between 170 and 180 centimeters, and 6 students fell into that bin. So here you see that by categorizing my continuous variable, I'm able to plot it in a way that's very similar to a bar chart. And to indicate that this isn't a bar chart, I make sure that the bars are touching to communicate that this represents a continuous variable. As a brief aside, while histograms are very popular, there are other ways to resolve the issue that it's hard to plot values for a continuous variable because every value is unique. A different solution is the density plot. The density plot smooths out the values so that you can obtain a continuous line that summarizes the scores in your data set. So what we see here is a density plot, and we see that it generally follows a similar shape to our histogram in the previous slide. And that is because this density plot shows us the same data, but instead of artificially categorizing it, it smooths out the differences between students' heights. So what we see here is that a height of 140 centimeters is more common than a height of 120 centimeters, which makes sense. And we see that a height of 180 centimeters is even more common, and heights drop off rapidly after that, with heights around 220 being very uncommon. The y-axis in a density plot is called density. How should we interpret this? Well, you should think of this as a way to distribute 100% of my sample under the curve. So in other words, the area under the curve of the density plot represents 100% of the observations in my sample, and that percentage is moved around to represent which values are percentually more likely, which is values around 180, and which values are percentually less likely. So you could take a slice of the density plot here and say, well, about 40% of scores lie between this boundary and this boundary. One pragmatic reason why density plots are less common than histograms is because they're not produced by default in SPSS, which is one of the most commonly used statistical software packages in the social sciences. On to the next topic, measures of central tendency. These tell you what is the most likely score to expect in your sample. We'll start with the mean, which you can think of as the mathematical middle point of your sample. We calculate it by adding up all of the scores in our sample and dividing that total by the number of scores in our sample. That makes it mathematically the middle point of the data. Here's a formula for the mean, and we represent the population mean with a Greek letter mu. It is a sum, sigma, from I is 1, that's participant number 1, up to capital N, which is the total size of the population, of the scores for individual sub I. So this is a sum across all of the observations of people in my population, divided by capital N, which is the size of my population. And if we calculate the mean for a sample, which we're doing today because we're doing sample descriptive statistics, then we use a Roman capital letter M to signify the mean, or we can use X bar, X with the bar on top. And that is a sum from individual I equals 1 up until lowercase n, which is the sample size, of the scores on variable X for those individuals sub I, divided by the sample size. So you see that the math is the same, but if I want the mean for the population, then I have to sum across the scores of all people in my population. And if I want the mean for the sample, then I sum across all scores in the sample. The mean has several key properties. If I take all of the scores in my sample and I add a constant value, so for example +2, the effect this will have is that the mean will also be 2 points higher. If I multiply every score with a constant c, so for example I multiply every score with 3, then the effect this will have on the mean is that it will also multiply the mean with constant c. So in this case, it will be the mean times 3. If I change just a single score by some difference value delta, then the effect on the mean is that it becomes delta divided by the sample size bigger or smaller. And if I add or remove a single score with an equal value to the mean, then the mean remains unchanged. Here's a visual example of how to calculate the mean. On the screen you see a black number line which ranges from about 3 to 10. And we have 5 observations indicated by these orange dots. There's no y-axis here, these are just single observations along a number line. So we have one person with a score of 3, one person with a score of 4, 6, 7, and 10. The mean is the value that is mathematically in the middle of these scores. So in this case, the mean is 6. And what I mean when I say the mean is in the middle is that the distance of the points to the left of the mean in total is equal to the distance of the points to the right of the mean. So these black lines here indicate the distance of each observation to the mean. And if I were to add up the distances on the left, they would be the same as adding up the distances on the right. So the mean is in the middle. Numerically, we compute the mean by adding up all the scores. So in this case, that would be 4 plus 6 plus 7 plus 3 plus 10. Those are my observations, divided by the number of scores, which was 5, which gives us 30 divided by 5, or 6. The mean is 6, which we can verify in this plot. And like I explained before, if we were to add 2 to every score, then you can verify that the mean also is incremented by 2, so then the mean would be 8 instead of 6. And if we multiply every score by 3, these would be the new scores, and the new mean would be equal to 3 times the original mean, so also multiplied by that constant. If we are to change a single score by a constant, in this case plus 3, so we add 3 to the observation that was 10, then we add 3 divided by the sample size to the original mean to get the new mean, which is 6.6. And if we add a single observation with a score equal to the mean, then the mean remains unchanged. I want to briefly take an aside. Sometimes it occurs that you have multiple means for 2 different samples. And I want to explain how you can combine the means from different samples to get an overall mean for the samples combined. If these 2 samples differ in size, then obviously the larger group should influence the resulting total mean more than the smaller group. That's why we call this a weighted mean. So let's say we have 2 groups, and for both groups we've calculated a mean, m. So we have group A, for which we have mean sub A, and we have group B, for which we have mean sub B. To begin, we multiply both of these means with the sample size of their original groups. So we multiply the sample size of group A with the mean of group A, and the sample size of group B with the mean of group B. And then we divide the resulting sum by the total sample size of both groups, n sub A plus n sub B, and that gives us the overall mean overall. So for example, if we have one group with 12 participants and a mean of 6, and another group with 8 participants and a mean of 7, then we would multiply 12 times 6 and add 8 times 7 and divide by the total sample size of 12 plus 8 is 20. And we see that the resulting mean is 7.4. And that's skewed slightly more towards the mean of the larger group, because that group is more influential. If both groups have equal sizes, then you can just add the 2 means and divide by 2. You don't have to multiply out the number of participants. The next measure of central tendency I want to introduce is the median. You can think of the median as the rank order middle score of your sample. Another way to think of the median is as the 50th percentile score. What is a percentile? So the nth percentile is the score in your sample for which it is true that n% of the other scores fall below this score. So if you've ever heard someone say, I'm in the 90th percentile of intelligence, that means that 90% of people are less intelligent than this person. So for the 50th percentile, it is true that 50% of scores fall below that score. And that score is called the median. It is not defined by a formula, but by a position. To get it, you must order the scores, and then the median is the middle score. The median has some attractive properties because it is less influenced than the mean by skewed distributions, so distributions that are not symmetrical, and they are less influenced by individual outliers, so really extreme values. Think about income, for example. Most people make around modal, and then there are some very few people who make a lot more than that. If you were to calculate the mean income, then you would estimate the average person's income to be much higher than it actually is. because these few extremely wealthy individuals pull up the mean for everyone. But if you calculate the median, you get a much more realistic estimate because those few ultra-rich individuals don't influence the median as much. So visually, finding the median looks like this. These are the same scores on the number line that we examined previously, but this time I highlighted the median score in red. Note that I didn't put a big stripe through the number line because the median actually corresponds to one individual score. So instead of putting a line here at 6, I decided to highlight the individual whose score constitutes the median. Here's a different numerical example. Imagine that these are data that we collected. It doesn't matter for this example what the variable is. And these are the unordered scores. Now, if we were to order these scores, then we immediately see which one is the median. It's this one, 60. Because there are 4 scores to the left of it and 4 scores to the right of it, so this is the middle value. How to determine the middle value if your sample is large? Well, in this case, the sample size is 9. That's an odd number, so you know that there's a single score in the middle with an equal number of observations to the left and to the right of it. And then the median will be the n plus 1 divided by 2th score. So in this case, that's going to be the 5th score. So n is 9. N plus 1 is 10, divided by 2 is 5. The 5th score will give you the median. And that was 60. Sometimes we indicate the median as x with a tilde on top. Of course, it can also happen that you have an even-sized sample. So let's add one more score. Now we have 10 observations. There is no exact middle mark. We would again order all of the scores, but the median will now be the mean of the 2 middle scores, so the 5th and the 6th observation. So that is 60 plus 63 divided by 2. The median is 61.5. As I promised, the median is more robust to outliers than the mean. Let's examine this by adding a single outlier. So you see that all of these values are in the range of about 52 to 67. And now we add a score that's much larger, 720. But the median remains unchanged, it's still 60. If we calculated the mean for this sample, it would jump to 126. Notice how incredibly sensitive the mean can be to outliers. The final measure of central tendency we're going to discuss is the mode, and you can think of the mode as the most common score. Conceptually, if you have a discrete variable where each observation may occur more than once, then the mode is simply the value or category that appears most often. But for continuous variables, it's a little bit more difficult. You can think of the mode there as marking the peak in the distribution. So if we look here at this density plot that we examined earlier, then you might think the mode is about here around 180. And if you use a histogram, then you might say the mode falls between 170 and 180. The mode is the only measure of central tendency that's valid for nominal measurement level data. So for example, if you ask people their favorite color, you can't calculate a mean or a median, but you can report the mode. But you can also get a mode for ordinal, for interval and ratio data, even though, as I explained previously, it's very rare for interval or ratio variables to have the same score repeated more than once. So there you would have to look at the peak in a histogram or density plot instead. It is, however, very useful for discrete ratio variables. For example, number of children, that's a ratio variable. There's an absolute 0 point, no children. And the distance between levels is meaningfully the same. So 2 children is twice as much as 1 child, and 4 children is twice as much as 2 children. So you can report that the modal family has 2 children. That just means amongst families, the most common composition is to have 2 children. Here is our visual example with the number line again, and to indicate how we arrive at the mode, I added 1 score. So in this case, every number on the number line has only 1 observation except for the number 7, which makes the number 7 the mode, and that's why I colored these observations in red. So here's another example about number of children. Here we have a data set with children per family, 2, 3, 2, 4, 1, 2, 2, 3, 1, 2. We could calculate a frequency table, and then we would see that the majority of families has 2 children. So the mode is 2 children. Here's another example. Let's say we have measured people's favorite ice cream flavors. 3 people reported chocolate, 2 reported vanilla, 1 strawberry, and 1 mint. I actually made some mint ice cream yesterday. So here the modal favorite flavor is chocolate, but let's examine the hypothetical case where we add 1 more vanilla lover to the dataset. Now chocolate and vanilla are both modes. This situation is called a bimodal distribution. There are 2 modes. And yes, it can also occur with continuously distributed variables. There you would see 2 bumps in the distribution, kind of like a camel's back. The next topic we'll address is measures of variability, or measures of dispersion, or measures of spread. Those all mean the same thing. If measures of central tendency tells us which value is the most common, then measures of dispersion tell us how common the measure of central tendency is. Let's start with the most rudimentary measure of dispersion, the range. Conceptually, the range is just the distance between the lowest value in my dataset and the highest value in my dataset. It tells us the width of the distribution of scores along the number line. But the problem is that it's fully determined by the score of the individual with the lowest value and the individual with the highest value. And because of this, it's extremely sensitive to outliers and not sensitive to the values of any other observations in my dataset. You can compute the range by subtracting the minimum score of x from the maximum score of x. And sometimes you'll see the range reported as the minimum and maximum value. So if the minimum value is 3 and the maximum value is 10, then the range is 10 minus 3, which is 7. And here's a dataset that corresponds to that example. Now let's add a single outlier to the dataset. Let's say we add to this dataset the extreme value 42. Now our x max has jumped from 10 to 42 and our range has jumped from 7 to 42 minus 3 is 39. You see that the entire range just jumped, which illustrates how unstable the range is if there are outliers in your dataset. The range can be useful, however, if you have, for example, a Likert style scale for a questionnaire, where the answer should be between 1 and 5. If you calculate the ranges for all of the questions in your questionnaire, and one of them is not bounded by 1 and 5, then whoever coded your data might have made a mistake in data entry. So the range can be very useful for detecting mistakes in data entry. But if we want a genuine measure of dispersion, we can do better than the range. Let me introduce the deviations and sums of squares. The sum of squares is the total spread of all data points in your sample. It is an important intermediary statistic in calculating other measures of dispersion. Here is how we calculate the sum of squares. First, we begin by calculating the deviation for each observation. Let's call it d sub I. And we get the deviation by taking the individual score x sub I and subtracting the mean. I've already shown you an example of this, namely in this figure. Here, remember that I told you that each of these black bars represents the distance of a data point to the mean. Well, those distances are the deviations. So if we want to calculate how long this distance is, we just take this score and subtract the mean. So this score is 3, minus 6 is minus 3, and this score is 4, minus 6 is minus 2. So in total we have minus 5 deviances on the left side of the mean. This score is 10, minus 6 is 4, and this score is 7, minus 6 is 1. So on this side we also have in total 5 points of deviations on the right. And as I promised, the mean would be exactly in the middle with an equal amount of deviations to the left, which was minus 5, and to the right, which is plus 5. And that also illustrates the problem with the deviations, because if we want to calculate the total amount of deviations in a sample, it will always add up to 0, because by definition, the amount of deviations on the left of the mean will always be equal to the amount on the right. So if we sum all of the deviations, we will always have them cancel out and obtain 0. To avoid this problem, we square the deviations. This removes negative values and allows us to add up all of the deviations, whether they be positive or negative. So we do x sub I, the individual scores, minus the mean squared. And then we add the sum across our entire sample of those individual squared deviations. And that gives us what is called the sum of squares. So here are two formulas illustrating how to get the sum of squares. The first I think is most intuitive. Take a sum from individual 1 up until the total sample size of the individual score for that person minus the mean squared. And you can get the same number by taking the sum across your whole sample of the individual scores squared minus the sum of individual scores squared divided by the sample size. So let's look at a numerical example. Imagine that these are our data, 4, 6, 7, 3, 10. The mean is 6, as we've previously examined, and we can make a table where all of the individual scores are in the leftmost column. Then in the middle column, we subtract the mean, which is 6, from each of these scores, and in the rightmost column, we have the deviation. So here the deviations are minus 2, 0, this score is equal to the mean, plus 1, minus 3, m plus 4. If we add all these deviations, they sum to 0, which is correct, that is expected. But because we want to get a total of all of the deviations, we have to get rid of the negatives, and we do that by squaring the deviations. So here in the rightmost column, we see the squared deviation. Minus 2 squared is 4, 0 squared is 0, 1 squared is 1, minus 3 squared is 9, and 4 squared is 16. These we can add up, and then we get the sum of squares, which is 30. What use is the sum of squares? Well, like I said, it's an intermediary statistic for calculating other measures of spread. The most important one of which is the variance. The variance is just the average squared deviation. So in the previous slide, we calculated the total squared deviation in our whole sample. And if we divide by the sample size, then we get the average squared deviation. And this captures the spread of scores around the mean. Larger values for the variance tell us that the data are more dispersed, and smaller values for the variance tell us that the data is tightly clustered around the mean. There are two different formulas that I want to make you aware of. The first is for the population variance, indicated by a Greek letter sigma squared. And this is the sum of squares in the whole population divided by the size of the population n. The sample variance, or Roman letter S squared, is calculated by taking the sample sum of squares and dividing by n minus 1. I will explain in a second why this is the case. Note that the units of both of these variances are the original units of your variable squared. So if I measured everybody's height in centimeters and then I calculated the deviations, those deviations squared will be expressed in centimeters squared. And so is the variance. Okay, so why do I divide by n minus 1 in the sample? This has a complex reason which is related to something called degrees of freedom. The intuition behind degrees of freedom is that you cannot estimate infinite statistics from a limited number of data points. If I collect data on 3 individuals, I cannot estimate more than 3 statistics based on those unique data points. And we pay for every statistic that we estimate with a degree of freedom. So you can think of degrees of freedom as the tally of how many more statistics we can estimate with a fixed sample. So why do we pay with 1 degree of freedom when trying to estimate the variance? Well, notice that to get the sum of squares, we subtracted the mean from every observation. In a sample, we often estimate that mean from the sample. That is the first statistic we estimated, and that is why we pay with 1 degree of freedom. If we then try to estimate the sample variance using a mean that was estimated on the same sample, then we're going to divide the sum of squares for the variance by n minus 1 to indicate that we already estimated another quantity from the same sample. So think of the degrees of freedom as a counter of how many more things we can estimate based on the sample. And once the degrees of freedom reach 0, then we have estimated as many statistics as we had pieces of information. So we cannot estimate anything more. In the case of the variance, n minus 1 degrees of freedom remain because we've already estimated 1 statistic, the sample mean, which we need in order to be able to calculate the deviations. Accounting for degrees of freedom makes the sample variance S squared an unbiased estimator of the population variance sigma squared. Let's look at a numerical example. Again, this is our data set. So we can calculate the deviation for every individual and then calculate the squared deviation for every individual. We can sum all of the squared deviations, which gives us a sum of squares of 30. And then to calculate the sample variance, we take that sum of squares and divide by the sample size minus 1. So in this case, that is sum of squares of 30 divided by sample size of 5 minus 1 is 4. The variance is 7.5. And it is expressed in units squared. So whatever the units of x were, those units are squared for the variance. Finally, we get to the standard deviation. I've been making a big deal about these squared units, and that's because it's really inconvenient and counterintuitive to tell people, well, the average spread around my mean was x squared centimeters. It's very inconvenient. The standard deviation restores the original units of your variable by just taking the square root of the variance. So what does the standard deviation tell us? It tells us what is the typical distance of individual scores from the mean in the same units as the original variable. So because variance is expressed in squared units, we take the square root to get back the original scale. And this applies regardless of whether it's the population standard deviation or the sample standard deviation. You just take the square root of the population or the sample variance, and then you get back the original units. Conceptually, you can think of the standard deviation as the average deviation of individual scores from the mean. Mathematically, this is not exactly correct. Because the variance is computed from the squared deviations, extreme scores have much more impact on the calculation of the variance than smaller scores. In other words, extreme observations are weighed more heavily in the calculation of the variance. And that disproportionate influence does not disappear when we take the square root of the variance. And that's why, in order to be mathematically accurate, we say standard deviation and not simply average deviation, because it's not exactly the average deviation. And you can see this intuitively here in the table as well. You see that a score that is at the mean does not contribute at all to the deviances, and a score that is close to the mean contributes a little bit, but a score that is very far from the mean contributes very much. And that is because when you square values, their influence increases quadratically. So here's an example of calculating the standard deviation. In the previous slide, we found that the sample variance was 7.5. If we take the square root, we get a standard deviation, which is 2.74. So we can say that on average, individual scores lie about 2.7 points away from the mean of 6. In pictures, here are two different distributions of continuous variables. You see the red distribution that has a high variance or a high standard deviation, which means that it's more spread out around the mean. And the blue distribution is more peaked, and that means it has a small variance or a small standard deviation, and its scores are more tightly clustered around the mean. How do transformations affect the standard deviation? Well, if you add a constant k to every individual score, then the standard deviation does not change. You merely pick up the whole distribution and move it k points, but it keeps the same width. If you multiply every individual score by c, then the standard deviation is also multiplied by c. So if you double every individual score, then the standard deviation also doubles. And if you add a single extreme score, then the standard deviation can increase by quite a lot, because as I showed before, extreme scores have a disproportionate influence on the variance and standard deviation. So let's examine that. Here we add a constant k, which is 5, to every individual score. And we see that we get the same standard deviation after adding this value to every individual score. So the standard deviation did not change. If we multiply the individual scores by 3, these are our new scores, and the standard deviation is also multiplied by 3. And if we add a single extreme score, we see that the standard deviation increases tremendously, which again illustrates how extreme scores have a disproportionate influence on the variance and standard deviation because we square the deviations first. So here are some key takeaways from today. Measures of central tendency include the mean, median, and mode. They each define what the center of a distribution is differently. The mode is the only one that's valid for nominal variables. Variance and standard deviation both are measures of dispersion or spread. The range is also used, but mostly to quickly scan for errors in data entry. When we calculate the sample variance, divide by n-1 to get an unbiased estimator of the population variance. This is our first experience of degrees of freedom. And if you try to visualize a distribution, keep in mind that a larger variance or standard deviation means a wider distribution than a small variance or small standard deviation. I will give you one bonus slide in this lecture, and that is another type of visualization, which is called the box plot. Now this is kind of a historical plot because it's easy to calculate by hand from summary statistics, which is not the case, for example, for a density plot, which requires advanced computation. So what does a box plot show us? A box plot simplifies the distribution of a variable. In this case, the variable is height, and it has a thick bar in the middle, which gives us the median score. So this bar here is the median score, or the 50th percentile, which is also called the second quartile. A quart is 25, 2 times 25 is 50. And then this plot shows us the first and the third quartiles. So 25% of the scores and 75% of the scores fall below these boundaries. The box here, the blue filled box, ranges from the value of the first quartile to the value of the third quartile. So 25% of observations fall below the left boundary of the box, and 75% of observations fall below the right boundary of the box. And then we have these dashed line whiskers. These whiskers are calculated by taking 1.5 times the interquartile range, which is the distance between Q3 over here and Q1 over here. And then we have this single straggler out here, this one lone dot. Any individual observation that falls outside of 1.5 times the interquartile range is labeled an outlier in a box plot, and it is individually plotted out here. So this also allows you to get a sense of how symmetrical is the distribution, is the median in the middle of the box, are there any outliers, are there individual dots outside of the whiskers. So it has some diagnostic value. You tend to see it mostly nowadays as part of more complex plots, but in older scientific papers, this is sometimes reported as the only visual summary of the data, because back in the day it was easy to calculate by hand. So to allow you to understand the previous literature properly, I explained the box plot. Good luck in your tutorials and see you next week.